Hi, and welcome to the first lecture unit in lecture chapter 3, which is on fundamental properties of multiclass modeling and multiclass losses. So what I want to do here is I want to introduce a couple of loss functions for the multiclass case. I kind of already used those in chapter 2 when I was talking about tree stumps. And then I want to also again prove optimal models under these multiclass losses and make a couple of other very basic observations about these. So what's the multiclass classification scenario? Well, we already defined that. We have our input space X here, we have our output space Y, and the output space Y now consists not only of two classes, but potentially of more than two, and I will usually use this letter small g here to denote the number of classes that we have in our training data set in our task. Okay, and our goal now is to find a scoring or probability model here, F, that maps to a g-dimensional output vector where g is the number of classes. So that the expected loss over our random variable x, y is minimized with respect to a certain loss function. And we have already seen in chapter 1 that we can write that in this form here, where we are minimizing over our hypothesis space with respect to this guy here, where we here have the posterior probabilities of y being in class K given our feature vector x times the loss that occurs between our predicted score and a certain class K. Basically, we sum this up over all potential classes K. Okay, and because we usually do not know our underlying probability distribution, capital P, we minimize the empirical risk and therefore an approximation of that theoretical risk in that manner here. So far so boring. We considered all of that already quite in detail in chapter 1. And we already saw multiple losses for binary classification tasks in chapter 1, and I will now simply generalize those to the multiclass case. So we'll define these losses again on vectors of scores, vectors of probabilities, and vectors of hard labels. And for the binary case, we could normally get away with just a single score here for two classes or a single probability. Especially a single probability for two classes, because then the second counter probability is kind of directly implied. For G classes, these scores and these probabilities really will have to be vectors. A little bit of notation. So I usually will need something like one hot encoding for my observed class in these definitions. So I'll usually use some notation like this here to perform or denote such a one hot encoding. So this guy here is 1 if y equals k and it's 0 otherwise. So what I'm basically doing is I'm transforming my observations where I have a specific class here into such a vector of zeros and ones, where a 1 occurs exactly in that component here, which matches the observed class. And that kind of a super trivial thing. I just need this notation here later for the formulas. So, and before we start with more interesting and practical losses on scores and probabilities, which I will really minimize later on in practical models, again, I will introduce this 0-1 loss, which I can simply write down here also in this form. So this is just the number of this 0-1 loss is also in the multi-class case simply 1 if my predicted hard label does not match the observed label. And we already know that this optimizer here of the theoretical risk using this 0-1 loss is this base optimal classifier, which simply picks the class with the highest posterior probability given a feature vector x. And I've also shown that the optimal constant model under such a 0-1 loss is simply the mode of the observed labels, so simply the class with the highest frequency in the training data. Now, let's generalize the Brier score to the multi-class case. So what was the definition of the binary Brier score? So the definition of the binary Brier score was simply compute the squared difference between the posterior probability and the 0-1 encoding of the observed class. And we do exactly the same thing here for the multi-class case. So we sum over all of our classes for a specific observation x. We transform our class into such a 0-1 one-hot encoding. We take the difference with respect to the predicted class, square everything and sum it up. So that's again also in the multi-class case kind of an L2 loss between posterior probabilities and observed class labels encoded as 0-1. And again, we can now ask ourselves, what's the optimal constant model? So such an g-dimensional constant vector here that reflects or models these posterior probabilities under this multi-class Brier score function. And the proof is again super simple. I will not read this out. Simply compute derivatives with respect to this theta k guy here, set them to 0, solve for theta k, and what you will figure out is that again, completely unsurprisingly, the optimal predictor is simply the amount of observed, or sorry, the frequency of the observed classes for class clay in your training data set, which you can, for example, write down like this here. Now, a little technical comment here, maybe not, well, just in order to kind of avoid confusion later on if you do practical experiments with these Brier scores. So, if you compare the binary Brier score that I introduced in chapter 1 and this multi-class Brier score that I introduced in this lecture unit here, unfortunately, this multi-class Brier score is not a direct generalization of the binary case. So it kind of is, but up to a certain constant. So for two classes, for the binary case, obviously you can also use this multi-class Brier score, but if you do that, what you will see is that this multi-class Brier score is unfortunately twice as high as the normal binary Brier score. And I have proven this here on this slide. I will not read this out. It's also a pretty trivial fact that's simple to see by just comparing the two formulas. And I just want to make you aware of that. So the multi-class Brier score is not a simple generalization of this binary class Brier score. It would be nice if it is. Unfortunately, it is not. So the reason is that we defined here this normal Brier score simply as pi1 of x minus y, encoded with the 0 and 1 squared. So in order for this to match the multi-class Brier score, what we would have needed to define would have been pi1 of x minus y squared plus pi 0 of x minus y with a flipped encoding. So the whole reason is that in the multi-class case, for two classes, you have two square terms going on here, while for our normal binary Brier score, there was only one term going on here, with this pi 1 of x minus this 0, 1 encoding for the positive class. There's also a multi-class version for the log loss, which is also called entropy, cross-entropy loss, and that terminology we'll understand in the chapter on information theory. So how does that look like? So that is simply a sum over all of our G classes, where we use this 0, 1 hot encoding here for our classes times log pi k of x. And we have to negate all of these terms. And we can again demonstrate the optimal constant for under this multi-class log loss. Again, this is the fraction of observed class labels. Again, the proof is super simple and left as an exercise for the reader. And we will now put this multi-class loss here to direct use and show how we can define a multi-class classification system based on logistic regression with this, which is called softmax regression. Also, I should say that for G equals 2, now the log loss, or this multi-class log loss, is now really a true generalization of this binary log loss. And you can easily check this here on this slide. I will also not read this out. So that's a bit better than for the Brier score case. So we don't really have to, I don't know, for the binary case, make a special comment whether we're using this binary formula or this multi-class formula. They are both exactly the same. And the multi-class case is indeed a true generalization of the binary log loss.